Welcome to the discussion. Today, we're diving deep into a paper proposing a novel transformer-based approach for novel view synthesis, LVSM. The authors claim to minimize 3D inductive bias, a significant departure from existing methods. What are the key limitations of previous novel view synthesis approaches that LVSM aims to address?
Previous methods heavily rely on 3D inductive biases, incorporating predefined 3D structures and rendering equations. Think NeRF, 3D Gaussian splatting, 3D-GS, and their variants. While effective, these biases limit flexibility and generalizability. They struggle with diverse, complex scenarios that don't conform to the predefined priors. Even recent large reconstruction models, LRMs, while improving on architectural biases, still rely on representation-level biases like NeRFs or meshes, hindering their full potential. LVSM aims to overcome these limitations by adopting a fully data-driven approach.
So LVSM eschews these 3D priors. How does it achieve novel view synthesis without them? What's the core architecture?
LVSM leverages transformer networks. They propose two architectures: an encoder-decoder and a decoder-only variant. The encoder-decoder model encodes input image tokens into a fixed number of 1D latent tokens representing the scene. The decoder then generates novel views from these tokens. The decoder-only model is even more radical, directly mapping input images to novel view outputs, eliminating intermediate scene representations entirely. Both bypass traditional 3D inductive biases found in rendering equations and network designs.
The choice between encoder-decoder and decoder only seems significant. What are the trade-offs?
The encoder-decoder model offers faster inference due to its fixed-length latent representation. The decoder only needs to process a fixed number of tokens regardless of input views. However, the decoder-only model achieves superior quality, scalability, and zero-shot generalization, outperforming the encoder-decoder variant and state-of-the-art methods by 1.5 to 3.5 dB PSNR. It's a classic speed versus quality trade-off.
The paper mentions Pluecker arrays. How are they incorporated into the architecture?
Pluecker arrays provide a way to represent the 3D geometry of the scene implicitly without explicitly constructing a 3D model. LVSM computes pixel-wise Pluecker array embeddings for each input view, using camera poses and intrinsics. These embeddings are then patchified and concatenated with the image patches before being fed into the transformer. The target view is also represented by its Pluecker array embeddings, used as positional embeddings in the decoder. This allows the model to implicitly reason about the 3D scene geometry.
The paper highlights zero-shot generalization. Can you elaborate on this aspect?
Zero-shot generalization refers to the model's ability to handle a different number of input views at test time than it was trained on. LVSM, particularly the decoder-only variant, demonstrates strong zero-shot generalization, performing well even with a single input image or more than 10, despite being trained on 2 under 4 input views. This showcases the model's ability to learn generalizable priors from data, rather than relying on specific assumptions about the number of input views.
The authors mentioned training stability issues. What techniques did they employ to address these?
Training plane transformer layers proved unstable due to exploding gradients. They used QK norm in the transformer layers to stabilize training, a technique also employed in other large-scale transformer models. They also implemented gradient checkpointing, mixed precision training with bfloat 16, and flash attention V2 for efficiency. They also skipped optimization steps with gradient norm exceeding 5.0.
The results are impressive, particularly the decoder-only model's performance. What datasets were used for training and evaluation?
For object-level evaluation, they used Objaverse for training and Google Scanned Objects, GSO, and Amazon Berkeley Objects, ABO, for testing. For scene-level evaluation, they used the Real Estate 10K dataset. The results consistently show superior performance compared to state-of-the-art methods, even with significantly reduced computational resources.
The ablation studies are crucial. What key insights did they provide regarding the model architecture choices?
The ablation studies confirmed the benefits of the decoder-only architecture. Increasing the number of layers in the decoder-only model consistently improved performance, highlighting its scalability. In contrast, for the encoder-decoder model, increasing encoder layers negatively impacted performance, suggesting that the intermediate latent representation might introduce limitations. They also showed the importance of self-attention across all tokens and joint prediction of target image patches for optimal performance.
The paper mentions a significant computational advantage even with limited resources. Can you elaborate?
The authors demonstrated that even with only 12A100 GPS, a smaller version of the decoder, only LVSM, outperformed previous methods trained with far more resources. This highlights the efficiency and scalability of their approach, making it more accessible for researchers with limited computational capabilities.
What are the key takeaways from this research? What are the potential future directions?
LVSM presents a significant advancement in novel view synthesis by minimizing 3D inductive biases. The decoder-only architecture, in particular, demonstrates impressive scalability, zero-shot generalization, and high-quality results. Future directions could include exploring even larger models, investigating different tokenization strategies, and potentially integrating LVSM with generative models for 3D content creation. The ability to achieve state-of-the-art results with minimal computational resources is also a significant contribution. The paper mentions an interesting analogy between the encoder-decoder and decoder-only architectures and their counterparts in large language models, LLMs. Can you expand on that?
The encoder-decoder LVSM is analogous to the encoder-decoder framework in the original transformer and perceiver I/O models. The decoder-only LVSM resembles a GPT-like decoder-only architecture, but without the causal attention mask. This analogy highlights the underlying architectural similarities and the potential for transferring knowledge and techniques between the fields of computer vision and natural language processing.
The paper notes some limitations, particularly regarding zero-shot generalization to different aspect ratios. What were those limitations?
The model struggles with zero-shot generalization to input images with aspect ratios different from those in the training data. They observed high-quality synthesis in the center, but blurred regions at the boundaries of images with aspect ratios exceeding those in the training set. This is likely due to the training data being center-cropped images, resulting in a lower density of Pluecker rays at the boundaries.
This has been a fascinating discussion on LVSM. Thank you for your insightful explanations.